What happens when you have a logarithm and you multiply two numbers? What's the ln of a times b? What do logarithms do to multiplication? They change it to addition. This is log ln of a plus ln of b. And of course, we have to have a and b are both positive numbers here. All right, and this is the last one I'm going to prove, I think, but this one has an interesting proof. A little complicated, a little harder than things you've seen in the past. Let a be any fixed positive number. And consider ln of a times x, where x can be any number you want it to be, any positive number, and consider ln of a plus ln of x. What I want to do is I want to convince you that ln of ax is exactly equal to ln of a plus ln of x for any number x, in particular the number b, whatever the number b is. And here's how I'm going to do it. I'm going to take the derivative on this side. What's the derivative of ln of a times x? How did we take derivative of an ln thing again?
One over the inside of the natural log.
1 over the inside, so 1 over ax times
The derivative of the inside.
the derivative of the inside. And the derivative of the inside in this case is, remember that a is just a fixed number, so you can think of a as being like the number 7. And then this is an x. What's the derivative of 7x? 7. So what's the derivative of ax, where a is just a fixed number? It's just a. So the derivative of the left-hand side is 1 over ax times a. I can simplify that. That's 1 over x. And then how about the derivative of the right-hand side? What's the derivative of ln a? Keeping in mind that a is just a number. So if a is a number, if a is like the number 7, then this is ln of 7. What's the derivative of ln of 7? 0. Why is the derivative of ln of 7 equal to 0? The derivative of a constant, the derivative of a number is 0. So this is 0 plus, what's the derivative of ln x? 1 over x. So that's 1 over x. So these two things, this left-hand side and this right-hand side, have exactly the same derivatives. The derivative of each one is 1 over x. What can you tell me about two functions that have exactly the same derivative? Keep in mind, the answer I want is I want these two things to be equal.
Are we both assuming that they don't have like a plus c value?
So these two things are exactly the same with a plus c, aren't they? So if two things have the same derivative, they're not necessarily equal. They have the same slope, which means they differ by a constant. So for example, x squared and x squared plus 3 have the same derivatives, don't they? But they're not equal. So what I know so far is I know that ln of ax has to equal ln of a plus ln of x plus some constant. If two functions have the same derivative, that means they differ by at most a constant. What I'd really like is I'd really like to show you that this number c has to be the number 0. And if this number c is the number 0, then these two things are exactly the same, aren't they? All right, so I'm going to pick my favorite number in the world now for x. It's my favorite number in the world to pick for x. 1. Okay, so pick x equals 1. On the left-hand side, I would have ln of a. On the right-hand side, I would have ln of a plus ln of 1 plus c. However, what's the ln of 1? 0. That would be 0. So ln of a has to equal the ln of a plus some number. For that to be true, what does that number have to be? C has to be 0. So, ln of ax equals ln of a plus ln of x for all x. So there's that important property of logarithms. Questions on that? At the time when logarithms were invented, this little formula right here was probably the single most important formula in all of mathematics back when logarithms were invented. Anybody know who invented logarithms? A man named John Napier. Anybody know when logarithms were invented? Well, Napier was born in 1550, I believe, and he died in the early 1600s. So sometime in there, 1570s, 1580s, 1590s, sometime in there. Why was that important? That function, that rule right there, so very important back in the late 1500s? All right. Well, back in the late 1500s. There was one branch of science that was enjoying much more success than all the others. What branch of science was happening in the 1500s?
Physics?
Physics, some physics. Something else more important back then, though. Astronomy. What happens when you're dealing with astronomy? What kind of numbers are you dealing with? Big numbers, right? The distance between two planets is a big number, or the distance from here to the sun is a big number. So imagine now that you have two really big numbers. And of course, back in the 1500s, you didn't have a calculator either, did you? No. So you have two really, really big numbers. If you have two really, really big numbers, would you rather multiply those two numbers together? Or would you rather add those two numbers together? You would much rather add them. How come? It's a lot easier to add two big numbers than it is to multiply two big numbers. And that's what this allowed people to do. They had two big numbers they needed to multiply together. What they would do is they would perform a logarithm on those two numbers. And that converted the problem into an addition problem, which they could do very quickly. And then they would have to do something called an inverse logarithm to get back to the original answer that they wanted. But doing the logarithm and the inverse logarithm was much, much quicker for them than it was to multiply. And so this saved the scientists an exorbitant amount of time. They can now do a lot of addition instead of having to do multiplication. And also, more importantly, almost, rule number 10, ln of a over b. What happens when you have a logarithm and you divide two things? That allows you to change to subtraction. So same sort of deal. Instead of having to divide two very large numbers, they were allowed to subtract two very large numbers. And subtracting is much, much easier than multiplying or dividing. Okay? So that's why these logarithms became important. Napier, by the way, did not invent the natural logarithm. I forget which base he had. But for our purposes, as far as calculus goes, we like the natural logarithm. And we'll see why. We'll talk about logarithms of another base down the line here in a few days, but we'll see the natural log is better. All right, and then rule number 11. Again, I'm not going to prove this one either. What do logarithms do to exponents? They bring them down front. You can prove numbers 10 and 11 in almost exactly the same way we'd prove number 9. Write them down, take derivatives, and show that the derivatives differ by a constant, and then show that the constant is 0. Questions on those?